Hey guys, it's Keith here. This is a video that's a little bit of a deviation from my normal X-Lights videos, not that they've been that frequent recently. I've been playing with the twinkly lights and trying to understand a little bit about how they work, and so I wanted to spend a little bit of time going through that today. Now, to set expectations ahead of time, if you're going to watch this video, I have not completed reverse engineering and understanding the protocol, but I've made a fairly significant amount of progress. And if you're interested in hacking the twinkly lights and working out how to control them using something other than the controller that they come with, I think the presentation I'm about to go through will get you some way towards understanding how to do that analysis, and maybe even some circuitry that will help you along the way. So let me take you through it. So first of all, for those people unfamiliar with twinkly lights, Twinkly is a company, you search for it on Google. They offer these pixel lights here, which have got this really nice small form factor. The colours are quite pastel-like compared to regular bullet pixels, which are the most common pixels that are used in a lot of the lighting projects that I work with. So they've got a really interesting and nice form factor that looks much more like traditional Christmas LEDs, if there's any such thing as traditional Christmas LEDs, but more like the sorts of store-bought lights you would buy, yet still being fully RGB, controllable, able to run patterns, among other things. They don't just come in this form factor. Twinkly actually sell their lights in a number of different form factors. Have a look at their website. They are relatively expensive compared to a set of bullet pixels, which these days will set you back somewhere in the order of $20 to $30 US. The twinkly lights, and this is a pack here of 200, for me is $75 Australian, which is going to be at least $50 US. So they're not particularly cheap, but they are a very, very, very well built product. They come in lovely packaging. They're all beautifully bundled up with quality equipment. This is not a cheap set of lights. This is a really quality set of lights, which means it's a pity that I had to cut them up to do this analysis. What makes them different? Well, a couple of things. So there is the small form factor, as I said. So rather than being 12 millimeters, I don't know, they could be about a 6 millimeter or 5 millimeter LED. They're quite a small LED. They do come with a fixed controller. The controller is hardwired on. It doesn't disconnect in any way. And it is Wi-Fi only, which means that you typically would control it from an app on your phone. Maybe not just iPhone. I imagine it works with Android as well. I must admit, I just don't have an Android phone. It's primarily designed to run patterns. It does have a very, very capable spatial mapping technology, which allows you to map out where you've put your LEDs in both 2 dimensions and in 3 dimensions, and then overlay the effects onto those things. So it does let you do some pretty cool stuff, and multiple sets can work together as well, offering an even greater capability. Commonly used on, put it onto your indoor Christmas tree, map out where all the LEDs are, and then you can run patterns which appear to follow the tree, like bars, patterns going up and down, etc. All very cool, all run and triggered by the iPhone app. There is some ability to remotely send data. As a protocol, I don't think it's actually documented, but John Lord and others have done some work in terms of understanding that protocol by reverse engineering some of the network packets that go between the phone and the Twinkly controller, and have managed to build, in John's case, quite a powerful program that acts as an ArtNet bridge, where you use a lighting program like an X-Lights or a Lightorama or a Vixen to send ArtNet packets to John's program, which then translates it and sends the data out to the Twinkly pixels. There's also a little bit of capability both in X-Lights and Falcon Pi Player, or Falcon Player as it's more commonly known these days, to actually send data directly to the Twinklys as well. It's probably not as good as John's stuff. John seems to spend a lot more time keeping track of exactly what the capabilities are and troubleshooting it, etc. And so his stuff tends to be a little better. So if you've got more advanced use cases, you may want to go that way. The downside of it is it obviously requires you to run his program somewhere, which involves additional hardware, which you may not want to use if you're running a show from a Falcon player or something. It's just an extra thing to worry about. One of the things that does make them quite interesting is that they actually send both the power and data over the same pair of wires, whereas most of the bullet pixels that you will see have at least three wires, a positive, a negative, and a data wire that is where all the data is sent over. These only come with the 2 wires, which means one of them's obviously positive and one of them's negative, and then of course somehow there's a data signal that is sent over to it that the lights obviously respond to, and it's that I'm trying to reverse engineer here, and I'll walk you through what I did and what I found. So here are the lights. I've cut them up and I've put these JST connectors on it, which allows me to then put things in the middle. And one of the key things that I used was this JST connector here, which has a couple of bare wires on the positive and the negative, which enabled me to probe what was going on those twinkle lights, sending twinkly lights as the controller, which is this box up here, was sending data out to both this string and that string. So here it is. Hooked up. You can't actually see the connections, it's slightly off screen, but here's my scope here, and you can see the data signal or the voltage level that is sitting across those 2 wires. There's a very definitive maximum here, but it drops below the maximum quite a bit, showing the data signal. So if we zoom in on this and look at exactly what this looks like, here's the results that we got from my oscilloscope. So the top voltage is 24 volts, so they are 24 volts DC lights, and the voltage here is dropping down to somewhere around the 14 volts. But as you'll see in a minute, this is actually misleading, and I determined this a little bit later. If you zoom in on the signal, you see that the signal stays at 24 volts a lot, but then it drops away and then jumps back up to 24 volts and jumps away. And this is the thing that made me a little suspicious, that I wasn't seeing what was the real signal here. This looks a little bit like driving at 24 volts, then maybe turning the power off, but some capacitance in the circuit holding the voltage up, which then slowly degrades. And then at this point here, it turns it back on, so it jumps back up to 24 volts. And obviously, when you look at this signal here, you can see that although it shows all the same height here, in reality, of course, it's not all the same height. And that's generally because there's some larger gaps here where it drops down further. So I had removed the LEDs at this point, and I was just probing the wires as it was coming from the controller. Definitely very strange, very suspicious. So what I did was I reconnected the pixels, and when I reconnected the pixels, the signal changed quite dramatically. Instead of having all of that uneven signaling, I now had a real solid set of highs and lows, with a high at 24 volts and a low at about 10.2 volts. And when you zoom in on it, you can see that it is actually a digital type signal, albeit offset and much higher than most digital signals are. With most pixels, the digital signal is typically a 5 volt signal, which is a common TTL voltage. But in this case, it's over 10 volts in distance, and it varies. It's not a constant timing with the WS2811 pixels. Every bit takes the same amount of time to send. It's just a variation in how much of that time is high versus how much of that time is low. And as I went and looked further into this signal, it doesn't seem to work that way. The highs seem to be relatively consistent, but the lows vary. And so that's obviously how the pixels are reading the data bits out of the signal. So quite different. Now, obviously, in order to get something useful, it's hard to get something useful out of particularly a low-end oscilloscope such as this one. We really need to put it into a logic analyzer, and yeah, the bee's knees of logic analyzers, the Soleil, and I happen to have a Soleil, but if I was going to use that, somehow I needed to get rid of that 10.2 volts and make it 0 volts, and I had to reduce the 24 volts down to 0 volts. So here's the circuit that I ended up building to do that. It's actually quite a simple circuit, and I'll explain it to you. So you have your data in, so the plus 24 volts is coming in on the data in line, and the ground is obviously the other wire. I pass it through a capacitor. It's only a small capacitor, and what that does is essentially filter out all of the DC part of the signal. So you end up with a signal that actually varies still by 20 volts, but actually it ends up being between minus 10 point something, minus 12 volts and plus 12 volts, going backwards and forwards. And so in order to get that to be an all positive signal, there's a signal diode here that sits across here, and that just gets rid of the negative part of the signal. So at this point I've got a digital signal, but the digital signal has a voltage difference that sits at something in the order of 10 volts or so. And so there's just a voltage divider here that both reduces the current because it's quite high resistance, but divides it in half, and that essentially gives me something that's pretty close to a 5 volt output that I can then pass into my Soleil here and start to capture the signal. And here's a circuit that's just thrown together on a piece of breadboard. It's not built neat or anything, it doesn't need to be. The capacitor, the diode, and the voltage divider with the two 10K resistors here. The data signal comes in the orange wire. This wire here is actually blue, it looks a bit green. That's the ground wire that connects to both the pixels and also to the Soleil. And then there is this one here, which is the data wire, which connects to one of the data wires on the Soleil so that I can capture the signal. So this is what you end up with when you start capturing the signal, and as a waveform it's got a number of interesting characteristics to it, which I'm only going to touch on briefly here, highlight the major features. This here happens to be the start of a frame. It's got this rather long pulse and a low pulse, followed by a set of data. You can see that the data is further subdivided into what I call words. Those words actually look like they're 34 bits plus a terminator at the end, and I'll go into the timings on those in a minute. The frame itself takes about 40 milliseconds for these particular pixels. I think they're 200s, I mean they could be 300s, but there's something in the order of that many pixels. And this is a count. There's 4,376 rising edges within that frame, and so basically I'm measuring from the start of this signal to the start of the next one. That's all the timings here that you can see. This is the same thing, but here I'm zoomed in on one of these words. You can see that there's 36 rising edges in this case. That's because it counts the extra one here. It's actually 35, of which 34 are data. I'm not counting this last one as a data bit, so I think it's about a 34 bit data signal. I have no idea what it means. I have not done the work yet to try to decode, what's a 1, what's a 0, and how do those 1s and 0s and what combinations of them affect the LEDs in what way. So zooming in, so here what I've done is I've zoomed in even further and started to capture some timing. So the frame starts with, as I said, this long pulse followed by a long low. The long is 32 microseconds, the low is actually 27.25 microseconds. After that, you get 32, it's not 32 bits, it's 34 bits. So a frame is a series of words containing 34 bits. The bits seem to be either 5.25 microseconds high and 5.2 microseconds low, offering a frame time, a bit time of 10.5 microseconds, or they're 5.25 high followed by only 3.25 low, making a bit time of 8.5 microseconds. So, postulating here, these could be 1s, these could be 0s. Of course, it could be the other way around. Or it could be an even more complicated coding scheme. I just don't think so. I think that's probably what it is. That would be my hypothesis going into it. And when you get to that very last bit, the uptime or the rise time there, the high time is only 2.25 microseconds, and then you have basically a 10.25 microseconds low time at the end, which indicates the end of the word, and then the words repeat until it's done. Again, purely speculating. Look, I assume each one of these words represents a pixel. I don't know that that's the case, but it seems likely just based on the way in which most of these protocols, and I've implemented a number of protocols across a number of pixel types, and that's typically how they would work. So, what am I doing? I'm going backwards. We don't want to be going backwards. So what do I need to do, or what comes next? Really, I need to do two things. First of all, I need to understand the protocol. Now, there may be documents on this on the web. I don't know. I haven't found any. I must admit, I didn't spend a huge amount of time searching for them yet. But it's, in my experience, it has been kind of hard to find similar pixels. I've never seen these pixels commonly for sale directly just as an underlying product on AliExpress or one of the other Chinese websites. It is entirely possible that there is a vendor out there that sells them, but it's also entirely possible that they're designed and made purely to the specifications of the Twinkly company, and therefore there is no documentation on the protocol, and the only thing the only thing that's going to understand the protocol is basically spending time sending data at it, monitoring how the pixels respond, and try to work out what things mean. The second thing I need is a microcontroller program to generate that digital signal, with something that is sufficiently close to the timing that I've captured on the Soleil. Now, I have actually written something that runs on a Raspberry Pi Pico that kind of does that. It's definitely not finished yet. It's got a few quirks that would cause a problem, I think, if I tried to use them on a real pixel, but I'm definitely making progress on that front. And finally, I'm going to need a circuit that will take that digital signal out of something like a Pico and turn it into that 24 volt, 10.2 volt data signal, which can both power the pixels and also control them, which is, and that's going to require a circuit that would actually do that, which fortunately I've designed. Now, I haven't tested it. I definitely haven't tested this with real pixels, and so if you use this circuit, you're doing it at your own risk. I have tested it using the 1 kilohertz signal that comes out of my scope, where I've put the 1 kilohertz signal in the data in, and I've monitored the output, and I do end up with a signal that it does switch roughly between 10.2 and 24 volts. It's not perfectly clean. It definitely doesn't look as clean as the signal that the Twinkly is, and so it is possible that it could damage your pixels. I also haven't put a load on it, so I don't know how this will perform under load and whether the waveform will distort to the point where it's not useful. All of that's unknown, got to be tested at some point. To walk you through it at a very high level, and you can see this in a picture, I effectively have a bench power supply that provides 24 volts into this buck converter, and then the buck converter outputs a 10.2 volt signal, which is this second power supply here. The main 24 volts is also needed, so you've got two voltages with a common ground that come into this circuit. The data comes into this MOSFET, and this MOSFET essentially does two things. It inverts the signal, so where the signal is coming in high, it makes it low, and vice versa. But it also uplifts the signal to that 10.2 volts. So I've now got a signal that's inverted with a 10.2 volt throw. That then goes into two MOSFETs, this one and this one. This MOSFET here controls the 24 volt output. So again, this is an inverting MOSFET, so I end up with a 24 volt signal where the data at this point here is 24 volts whenever the data on the input is high. And the signal also goes into here, and this here is a non-inverting MOSFET layout. And so what this does is this passes the 10.2 volts, which does actually drop by 0.6 volts. So you're probably going to have to run this at 10.8. passes it through this MOSFET and out to exactly the same connection. And this does exactly the opposite. When this signal is low, this allows the 9.6 or 10.2 whatever volts through, which is exactly the opposite of what this MOSFET does. So together you end up with a signal that jumps between those two voltages, and because there is a slight difference here, because this obviously goes through 2 transistors versus this goes through 1, and so there is a little bit of latency there. But based on the signal that I've seen, it's not too bad. You do get some negative going spikes here when it switches to 24 volts, and that's just because it takes a little bit longer for the 24 volts to kick in than it does for the 10.2 volts to switch off. Fixing that, I have actually put a capacitor across here as well for a couple of reasons. One is to fix that, those spikes when it does drop a little bit low. But the other reason I put the capacitor in is clearly when we looked at the signal without the load on it, there was clearly capacitance there, and so it sort of made sense to me to put a small capacitance on the output. And when you probe this again, you without a load on it, it also looks like that. You get that capacitive fall off, etc. So it's probably not perfect, but it's pretty close, and definitely a starting point for the next phase of the work, which is to start to try to simulate sending data to the pixels and see whether I can get the pixels to actually respond to a data signal that I produce. So that's where I'm going next. Finally, there may or may not be a part 2. It really all depends on whether I can actually work protocol out. I'm not sure that a part 2 video where I ultimately fail will be that useful. Maybe it will, maybe it won't. And it all depends on when I get that done. We're about to enter into Christmas season. I've got a Christmas show to get up. I've got travel to do. There's a whole bunch of stuff that's going on. So I'm not sure when I'm going to get back to it. But yeah, when I do get back to it and do manage to get something working, etc., I'll make a similar video that closes that out. Of course, people watching this video may be interested in helping out. You may have information about the protocol. You may have already cracked the whole thing, and this may be duplicative work that someone else has done, in which case please share with us any links or other things that you might have to work that you've done that's done that. And if you haven't done that but you're interested in building the circuits, trying it out yourself, maybe spending some time and actually make some progress, would love to collaborate with others on this. Obviously I'm not looking to do anything with this. While I do love the Twinkly lights, they are very expensive, and I'm not sure I would run significant numbers of them in my show. Obviously you would need to do a fair bit to actually turn this into something, building the driving circuits, building the microcontrollers, etc. So it's a non-trivial project for someone that really wants to take it the whole way. But when I first started in the lighting hobby, I was inspired by a guy who went by the handle Deepak that hacked the original GE color effects lights and documented the protocol, and inspired me to get some of those lights and to get an Arduino and see if I could get them going. And if this video inspires some people to actually spend some time and hack around and learn a little bit and generate an interest, well, then I think it's all good. So hope you guys enjoyed the video. Like and subscribe. If you've got any questions or whatever, please post them below the video and I'll do my best to respond. Thanks guys.